In this video, let's spend a minute to discuss how addresses are bound to variables. So obviously we write programs in terms of variables. Variables are data. Well, if data is data, that somehow implies, right, that we need to store it somewhere in main system memory. Now for us as a programmer, we're used to basically symbols, right? So we have, X and Y as being variables, right? One that I'm apparently reading from, one that I'm apparently writing from. As an FYI, this symbol here is basically like a very generic assignment. I didn't want to make it specific to a programming language here, so I use that. If you ever take a class in compilers, you'll notice that when they talk about programming languages in general, right, or if you take a programming languages class, they'll use that symbol, right? Kind of the colon equal sign will signify assignment, rather than equality, right, which is just a single equal sign. So yeah, normally we think about variables in terms of just X and Y, right, as being these symbols. But because they're variables, they have to live somewhere. So how do we deal with that? So somewhere, right, basically behind the scenes, my program will basically identify what variables are out there, and then based on what variables are out there, kind of try to compute basically an offset. So you guys have probably seen before the idea of a stack frame. So the idea of a stack frame, right, I actually talked about it a little bit in this class even, but you should have seen it in previous courses as well, is that I have the stack, right, that basically represents me calling functions. So program A calls A, right, A calls B calls C. And so we have this stack memory style of memory management, and then there are a bunch of different variables. So for example, maybe A has X, A has Y, that type of deal. Well, what happens inside, right, is we need to somehow translate that X and Y inside of my program to my actual addresses. And so they'll basically get rewritten. They'll be rewritten to be a little bit, well, to be a little bit symbolic, right? They'll basically be in terms of some sort of offset or some sort of start. So I've rewritten it over here, right, to basically say that this thing over here, right, my X and Y over here, this gets translated somehow, right, into this bit over here, right, these two things here. It's kind of split across the line. Basically what we're saying is that, X, with respect to this stack frame, right, we're being very specific here actually, X with respect to the stack frame is basically at plus 10, well, Y of the stack frame is in terms of plus 24. That's our what our model here is showing. So our idea there, right, is we're kind of dropping out, right, at least the letters, right, and now we're being a little bit symbolic. So rather than saying it's X, it's really the memory location at plus 10, right, or instead of Y, it's the memory location at plus 24. And these are what we call reallocatable variables, relocatable variables. The idea here, right, is that we're going to basically have these be a little bit dynamic, because I don't know ahead of time where my program is going to be stored in memory. Right, I have issues where if I assume it starts at the very beginning, well then that means it's like, well, I might overwrite something else, right? So my operating system normally should be in charge of deciding where in memory my program is going to be stored. And so that's going to be represented symbolically by that start variable. So it's like, well, your program starts here. I decided to put your program here, so your start is 10. And then from that point, right, basically we can do the math here and say, oh, it's going to be in location 20, location 34, right? I basically add those values up. The point is I need to support some sort of a dynamic location in my program for my program to be stored in memory, and so I need to do this symbolically, right? I need to have that kind of start offset that's still kind of included in there somewhere. And so yeah, the operating system, let's see, go down to the next bullet point. The operating system basically picks a location for the memory right here, right? I basically picked the location to be 1000, right? And then you can see that basically that previous line, right, gets kind of updated to look like this, right? This stuff kind of gets mapped downwards, right, as we substitute in start for an actual real value. And I already kind of mentioned this in text, right? So in all the operating systems, they used to kind of use kind of a constant for where in memory something would get loaded. The issue there, right, is that you can only load one thing at a time. Otherwise, things will try to overwrite them. To dive in with basically the diagram a little bit, this stuff over here, right? So this is an image we've talked about a little bit before. Basically, of the process why something is loaded up. This little process here, right? This stuff is basically corresponds to these symbolic locations, right? So this is we'll just write symbolic location over there. Versus over here, this is kind of actual locations. So the bottom right is the actual address, right? So over here, 1010, 1024. Versus up top is, start 10 plus start, or start plus 10, or start plus 24, right? Are the top parts. It's once your program is loaded and your OS is told where it belongs that you can actually fill in the blank and figure out what address it belongs at. All right. So that's kind of our overall kind of idea for how we kind of simulate variables and memory addresses. The final note here is that sometimes in our programs we end up basically, well, we may basically want to choose to store this in a register, right? So our offset where things start. The reason being is that if I move a program around, I want it to be able to adjust. So if I move a program from an address 1000 to 2000, I want it to still work. There are kind of use cases for that, and we'll talk about them later. So sometimes, right, it's useful to basically leave that as kind of a dynamic thing, right? So sometimes we'll set aside a register Well, I have basically a base register that can tell me where the process is located, right? And then it can from that compute the exact addresses for where it wants to store stuff. All right, so let's introduce a couple terms here in terms of addresses. The terms I want to introduce are basically a logical address and a physical address. So the first idea here, right, is of a logical address. A logical address is basically the address that's seen by your program, right? So your program lives in this world where it sees, stuff starts at address 0 and then it goes up, right? So it thinks it lives all by itself. Those are logical addresses. And logical addresses usually behind the scenes have a little bit of logic or math which happens, right? They basically analyze by the CPU, and from them I compute what's called a physical address. A physical address is an actual address on the, in RAM somewhere, right? So it's an actual physical thing, right? A logical address is kind of this, mystery number. Well, not mystery number, but like just a number, a virtual number maybe. Sometimes they're called virtual addresses. But like a virtual number which represents, this is what the program thinks. It thinks it wants to access something at, address 100. Then some stuff happens behind the scenes where the CPU has to translate that number 100 to be something a little bit more realistic, to be somewhere, specific in memory. The mapping there, right, is basically done by something called the MMU, so the Memory Management Unit. Basically, that is a little bit of hardware that's in charge of mapping from a logical unit to a physical unit. This bit here, right, and the logic behind it is what we'll spend a lot of time talking about. We'll introduce 3 different mechanisms, so contiguous, segment, and paging, for basically how do I translate my logical addresses into my physical address. And all those will kind of be building up, right, and they kind of get faster each time. Here, right, to introduce a little bit more vocabulary, we have the idea of a space. So sometimes I'll say something like logical address space. What that means is all the addresses available to a process. Or I might have something like a physical address space. What physical address space says is all the space available to a particular process, right? Well, available on a particular system, right? So it's like all the RAM that's available. Typically what happens is my physical address space is pretty small because it's like 4 GB, 8 GB, 16 GB, right? It's not that big. Versus my logical address, right? What my program basically sees unlimited memory. So it may be, 4 TB or something like that, right? It's really huge. So yeah, those are when I use that word space, we're just referring to everything that a program would possibly address, even though it may not exactly exist. Versus what exactly can I physically address, right? So those are kind of different terms. The simple MMU approach, right, which we'll talk about first, is basically to add the base to an offset, right? So it's like adding that, that it was like start plus 10, right? It was the thing we had before, and then eventually start got substituted to 1,000. So that's kind of the simplest operation, but again, we'll build on that. So overall, I just keep this in mind, right? Logical versus physical. It's the addresses the program sees, right, which are kind of virtual, versus the actual addresses that your hardware owns, right? Those are the physical things that you're obligated to actually store information into.